Thank you for attending to coming to our seminar. So the speaker is Daly. So he's a PhD student at Stanford, and he's working with several things on how to have an agile hardware flow. So working with core IR and some other tools that we are very interested here because we have some related work and we keep following this work. So thank you for coming to give a talk, and go ahead.
Yeah, well, thank you for the introduction. Yeah, so maybe just a little more background about myself. I went to Carnegie Mellon doing ECE, and after that I worked at NVIDIA for a few years to kind of dive into the industry of chip design and see what's happening there. And actually from that industry experience has really kind of motivated me into doing the work I'm doing in my current PhD, mostly because, oh, the tools are not that good in industry, and see how we can improve these. And also my advisor is Pat Hanrahan, who is also very interested in this. So yeah, just as an overview of my talk, I'll go through a little bit of kind of the history of our hardware group at Stanford. And then I want to talk about a kind of general approach for designing and using accelerators. And then I'll talk about basically Stanford's endeavor to design and evaluate coarse-grained reconfigurable array accelerators for both RTL and compilation. So one of the main things I will get out of this is that needing to essentially generate or co-design the compiler alongside the accelerator at the same time is very important. And then I'll talk about basically the numerous domain-specific languages and IRs that kind of enable this flow at Stanford. And then I'll do a little bit kind of lessons learned and some cool results as a result of this, doing some design space exploration on these accelerator architectures. So first, AHA, which is our hardware group, it stands for Agile Hardware Project, which in my opinion is one of the worst acronyms of all time. Agile Hardware. This is Mark is a very smart person, but potentially not at naming naming certain things. But it started in 2017 with the goal of kind of making hardware fun again and flipping the script on the hardware design lifecycle. And the group started off with only a handful of students, myself included, led by Mark Horowitz, Pat Hanrahan, and Clark Barrett. And now we have a whole lot more students with 3 new professors involved, Priyanka Raina, Kayvon Fatahalian, and Fred Kolstad. And really the real origin of this, basically when Pat is just a hacker. If you've ever met him, he will be at any free time, he'll be in his room coding about on some little project. And at some point in time, he decided to try out some hardware design. And he basically tried to use the Xilinx toolchains and just got super frustrated and decided that one of his major goals for the next 5 years was to kind of make some contributions into improving toolchains for hardware design. So I think that's kind of a interesting origin story of this group, with basically Pat being annoyed at the current state. So yeah, the goal of the center was to refresh how people do hardware design, specifically to apply modern software practices to hardware design and verification. And this pitch is probably very close to home for most of you working on hardware tools today, especially this group. And our main tenets, which guide our projects, are essentially to be open source when possible, use agile flows instead of waterfall flows, and to leverage domain-specific languages for efficient design. And our biggest result is an end-to-end system which can compile halide image processing DSL to a custom-built coarse-grained reconfigurable array, or CGRA. And we've actually taped out silicon and built this compiler toolchain with almost entirely our tools. So I probably actually don't need to pitch this too much to your group, but just to go through it, one traditional approach to designing accelerators is the waterfall approach, which is probably well known. And first, application or set of applications are analyzed. Then based on the characteristics of these applications, architects will design an architectural spec. Then the RTL designers and testers will go off and actually build and validate the thing. And finally, the physical design team will take the design to tape out, and a software team will build a compiler toolchain to target the accelerator. And as you see in these dependency links, there's two important observations here. First, that final step of writing the software and compiler often takes much longer than potentially than the hardware design itself. And this step is often delayed or thought about later in the process. And I did actually see this pretty often in my industry work. And also, since each of these stages takes several months potentially, iteration on this process is quite difficult. For example, if a new application arises that you want your accelerator to target, or the architectural requirements change, parts of the design will have to go back to the start of the waterfall and you're kind of hosed. So instead of the waterfall approach, we're adopting a more agile approach to accelerator design, where we start with a baseline hardware design and software compiler that just works. And it's a very basic design. And then as our applications change, we can profile the accelerator, run and get literal performance numbers, generate new requirements, and then update both the hardware design and software. So this sounds like a pipe dream, but so to actually make this work, we have to fundamentally update the way we approach design. The term co-design is often used here, but what does this actually mean? First, we propose that the accelerator itself is configurable, so we can map new or modified applications to it, even if they do not perform super well, as long as they can run. And most importantly, the hardware and the compiler that maps to it must evolve together. And even better, changes in the hardware design are automatically reflected in the compiler. And most of my talk will actually be on this idealized version of that, of this, where single changes kind of are reflected in the RTL generation and in the generation of the compiler. So let's talk about meta-compilation in the context of hardware accelerator design. Note that the next few slides are abstract to kind of arbitrary accelerators, then I'll bring it back into what we're actually doing. So first, as input to your meta-compiler, you provide some sort of chip specification. This will basically include all the possible parameterization of your particular family of accelerator. For example, number of levels of memory hierarchy, size specification of each memory, what compute resources you have, interconnect, all that stuff. And in some sense, this is just a high level kind of a list of all of the design decisions that a chip architect would come up when designing a new chip. And the interesting thing is if we keep all these decisions as essentially free parameters in a programmable fashion, we can potentially develop a meta-compiler flows. So first, we would want a flow which takes in all these decisions and generates the chip RTL itself, which I am referring to as the hardware meta-compiler. This is a programmer flow that takes in the chip specification and produces the RTL. You can also think of this as a generator in the most basic sense there. And then finally, the RTL and ideally physical design info will then be pushed through a traditional ASIC flow in order to tape out a real chip. And very importantly, alongside this, we also need to be able to configure the chip to run our applications. So in an ideal world, we can use our software metacompiler to essentially generate a chip-specific compiler that compiles and runs applications onto the accelerator. And I also want to note that to really complete this picture of the metacompiler, we'd also want potentially a runtime metacompiler that can automatically generate all of the drivers and APIs, et cetera, in order to actually execute stuff onto the chip, which is slightly separate from the software metacompiler. So I want to talk about kind of what we are doing at Stanford that approaches this this kind of mindset and framework here. So what we're trying to do at AHA, our goal, like many other labs and companies, is to accelerate certain classes of applications by designing hardware accelerators. Also, like many other labs and companies, we are currently targeting ML inference, vision algorithms, and image processing applications, for example, like camera pipelines. In particular, and in the future, we're also taking a host of new applications, including audio, crypto, and sparse. Fred Kolstad has been really important on the sparse acceleration front. And I also want to note that we are specifically targeting applications that are written in Halide. So Halide is just domain-specific language that I'll talk about a little bit more in a couple slides and describe it, but all the applications will be represented in this one domain-specific language. And I think very importantly, we do not know what the best hardware accelerator is for any of these domains. This kind of goes along with the agile mindset of iterating quickly to try out many designs and to evaluate them to see if they are good and see what they do, and then have a quick short iteration loop where we can see what's wrong and see what part of our evaluation is wrong, and then update it quickly, and then test out a new design. On top of this, best accelerator for one or more target applications is almost surely not going to be the same for other target application domains. So something that is good at ML inference might not be good at crypto, for example. But importantly, we have put our money on the general family of accelerators called coarse-grained reconfigurable arrays. So all of our work has been done assuming that our accelerator is going to be this coarse-grained reconfigurable array. One can question that decision up front, and there's good discussion on terms of like whether or not that is the appropriate family to start targeting for these domains or not. But we constrained our problem essentially to only target these coarse-grained reconfigurable arrays. So what exactly are these CGRAs? So essentially, the architecture is basically a coarser grained version of an FPGA, whereas FPGAs are like field programmable gate arrays are kind of programmed at bit level precision, so you can kind of configure exactly what every single bit is doing using lookup tables and then direct bit level routing. A CGRA is configurable at the word level, so where word means either 16 bits or 32 bits or something that's more coarse grained than a single bit. And in addition, we also have the ability to potentially support multiple bit widths, including a single bit or word level. And so this coarser grained reprogrammability reduces the power and area overhead while still having enough customizability for a broad range of applications. And so these CGRAs contain many computational resources called PEs, or processing elements, a very generic term that's used in a lot of accelerators. And these could be completely homogeneous, so the same throughout, or heterogeneous, so where we have multiple different flavors of PEs in our current CGRA. Similarly, it contains block RAM style memory tiles that could be as simple as just a single SRAM, or might have some kind of embedded programmable address generation logic in there, depending on what we want to try out for our CGRA. And finally, we have a routing fabric that is very similar to that of an FPGA. It just also has the ability to route word level data. So on top of this, we are essentially putting this CGRA into this is called an island style CGRA. And we're putting this into an ARM-based SoC with a second level memory called a global buffer. So this is kind of the design space that we're looking at for our accelerators. So let me talk about Halide, which is essentially the programming language that we want to target to run on our accelerator, or to accelerate on our accelerators. So Halide is a domain-specific language embedded in C++ that allows you to easily specify algorithms, especially ones that use stencil computations, in a convenient functional form. It was created by Andrew Adams and Jonathan Reagan-Kelly and has seen a lot of use. Google has most of their camera processing code using Halide, and there's an increasing community of people using Halide for expressing machine learning applications. And the really novel part of this domain-specific language is not the fact that you can easily express these functional stencil-like algorithms, but that it allows you to independently specify the schedule for the computational platform you are going to run on. So you might have a different schedule for running on a CPU or running on a GPU, or in our case, running on this CGRA accelerator. And so what Halide provides is these scheduling primitives that this includes when and where to tile your loop nests. So for example, like you can always, there's always the fun problem of like, make your matrix multiply run as efficiently as possible on there, and you're supposed to block it in a certain way and tile it in a certain way and reorder the loop nests. And all those kind of decisions are essentially high-level decisions that don't affect the actual fundamental algorithm itself and just should affect the performance. And so these scheduling primitives allow you to easily specify all those different things without affecting the correctness of the algorithm. Also, just note there's been a good deal of research in auto scheduling, and so automatically coming up with the best schedule for a particular hardware platform. And this is something we're interested in for our accelerators as well. So we notice that accelerating a portion of the algorithm onto a hardware accelerator should be as easy as using halide scheduling primitives. And this was work initially done by Jing Pu and Mark Horowitz. Each scheduling primitive has an interpretation in the context of our accelerators. For example, store at and compute at indicate which intermediates to materialize in which level of memory hierarchy. And unroll, for example, kind of indicates how much to use the PE computational resources in space or over multiple cycles in time. So let's plug in the CGRA family of accelerators back into our meta-compilation diagrams. So on the left, we now have a more constrained space of what possible permutations there exist for CGRAs, including the information about the second level memory, so like size and address generation logic for the global buffer, and then the whole CGRA fabric specification. So kind of what is in the PEs, what computations can we do, what bit widths can we handle, what do we have floating point, et cetera. What is the internal routing configuration within a PE? We have a memory tile specification, a routing network specification, IO, and a whole bunch of other stuff. And we know that the output of our software meta-compiler is itself a compiler that takes in the halide application and translates it into an FPGA-like bit stream for configuring our CGRA to run that particular application. And so a major idea that we have explored in order to facilitate a meta-compilation flow like this is to use targeted domain-specific languages as specification languages. So in particular, we have developed 3 specification languages at Stanford targeted for CGRAs. One for specifying semantics of memories called Lake, one for specifying the semantics of processing elements called Peak, and one for specifying the semantics of FPGA-style routing networks called Canal. Also, as an aside, as you may notice, we kind of have this naming scheme that is more or less geological features. And so basically when we tape out a chip, we choose a particular lake, for example. So like Lake Tahoe is our previous chip for our memory tile, and Mount Lassen for the peak, like a mountain peak, is for the current PE specification. And it's kind of useful to have that all consistent naming scheme there. So the way these programs written in the specification domain-specific language work is they act as a semantically precise single source of truth, which can be used to then generate a functional model, RTL, and the relevant compiler collateral, and even potentially a textual specification. And this single source of truth is, in particular, a very useful model to have, opposed to the more traditional flow of having an architect write out some textual design document, hand it off to different people in charge of manually coding a functional model, RTL, and then the relevant software artifacts. Whereas inevitably during testing, almost surely there will be mismatches between the functional model and RTL, and oftentimes it's not even clear which one is correct, and bugs can originate in either the functional model, RTL, spec, or any pair of the 3, or possibly all 3 might have a bug in it. And from my industry experience, these were always some of the most annoying bugs to track down and fix. So this single source of truth model does not have those issues or lessens those issues, other than the very real possibility of your generation steps being buggy. So as long as your generation steps produce semantically correct code, then you should only have one location where you have a potential bug in your code. And also the single source of truth allows a single set of tests essentially to be written for whatever the relevant portion of the specification is, that can ideally be run on both the RTL and the functional model at the same time, depending on which one you are working for. So that's been actually very useful to write a single set of tests that you can functionally verify and you can run on the RTL. Has been very useful for our validation effort. Also, as an aside, one of the chip companies I previously worked at, which may or may not be associated with the color blue, did have an interesting attempt at doing something along these lines where they would try to automatically generate RTL from an Excel or Word document specification. And it works surprisingly okay, but I would have loved to have been in that meeting room for the pitch of using that in your flow. So the notion of designing targeted specification domain-specific languages is only actually one instance of where this is used in our full ecosystem. This slide shows a non-complete set of other domain-specific language we have developed. in order to facilitate this project. And these include a Python-based hardware generation language, analogous to Chisel, called Magma. I'll talk about that a little bit more later. A staged verification framework targeting hardware generators, a polyhedral analysis scheduling tool, and an IR and compiler infrastructure called Core IR, which is kind of my major project. And all of these work together in coordination to create our full meta-compilation flow I've been describing.
I have a question. On
Yep, sure.
those languages like Halide and those things, do they go through Core IR? Or do
so I'll actually talk about that. And I'll show, my next slide will actually have the more kind of specific of how we're actually using this. But the answer is actually yes.
And then the other one that I didn't know is like you generate automatic documentation from the single spec?
We do that in one portion of it. That was a little bit more of an idealized flow, but okay. Yeah, oftentimes what we use is that single source is itself very readable, and we kind of use that a bit as the documentation. And and I'll show an example of like the PE specification language to show kind of what that looks like. But there's no reason that you wouldn't be able to generate something like some documentation for given the specification. Let's see. Yeah, one thing to mention is that most of our languages are Python embedded domain specific languages, and in general we kind of like Python for a multitude of reasons, including widespread adoption of Python, the ease of use, ease of ramp up for people learning some of our tools. Most people know Python, or it's easy to learn Python. And also there's some particulars about the flexible Python typing that makes it nice for certain properties of these domain specific languages. And one other thing to note is that most of these languages have basically just one or two core grad students as the developers for it, and kind of those are some of their core projects. And they're all open source, and I'll include some links at the end of this presentation. So using all these DSLs together allows us to create this kind of meta-compilation flow from the instance of the DSL. I know there's kind of a lot on this slide, so let me explain it slowly. So on the top left are the 3 specification programs, one for PEs, one for memories, and one for interconnect. And below that is our hardware compilation and validation flow, where we use our Python HDL Magma and our hardware compiler Core IR to generate the final Verilog for our CG array. We also use a tool called Gemstone to kind of bring a lot of the stuff together, but I won't talk about that too much. And then that final Verilog, which represents the chip design for the CG array, will be passed through an ASIC flow in order to do the full tape out for our chip. And then on the right side is the application compiler. So in essence, we compile Halide to a timing flexible Core IR representation, statically schedule it using our polyhedral analysis tool, scheduling tool called Clockwork. And then we go through what essentially looks more or less like an FPGA compilation flow with mapping, placement, routing, and bitstream generation. So like you mentioned, so the Core IR actually shows up in 2 places here. One is for the hardware generation portion, and one is for essentially the software generation, where we are leveraging Core IR in order to eventually generate the bitstream at the end to program the CG array. And then also, yeah, so importantly, the Peak and Lake programs themselves generate relevant rewrite rules in order to do the application mapping step of the compiler. So that's kind of the meta-compilation portion of this application compiler, where these specifications give the mapper essentially the tools in order to map to this particular version of our accelerator. And then similarly for interconnect, the interconnect will produce some collateral which represents a routing graph, so that we have a place and route tool that can eat that and then be able to place and route any application or compiled application onto the particulars of this thing. And just to reiterate, if we want to test out a new PE design, all we should need to do is update our Peak program. So we can update a couple lines of code to say, oh, I want to see what happens if I add this this new op in the PE, and to see how that affects the performance of the application. And ideally, that should be a one-line change or a couple-line change in the specification itself, and that should propagate to both the hardware compilation and the compiler compilation, really giving us this quick iteration that we desire. And be able to.
A quick clarification question. So, if I'm hearing you right, you're saying the specialization to the CGRA is done manually by using the DSLs of Peak or Lake or something like that. It's not coming from the halide.
Sorry, say that one more time.
So if your tool flow starts like a CGRA template, and then you give like a halide program you want to specialize for that. And so if I understand this example you just gave, are you saying that when you want to tailor the processing element for that program, that's done by a human, not from the halide program?
So just to be clear, the specification DSL literally describes the physical hardware itself. So you can think of the PE as describing like a mini processor within there. And that's kind of independent of the halide application in some sense. But there's a good question there of like, how can you design the PEs to basically best accelerate particular domain of applications? So if a particular set of applications has a whole bunch of fuse multiply adds, then you might want to stick a fuse multiply add as an inherent operation into your PE. So the application can inform the design of the PE, but there's no direct compiler line from the application to it. But this is kind of the whole why we want fast iteration. I'll talk a little bit about this kind of design space exploration at the end. Does that make sense?
Great. Definitely. Thank you.
Yep. All right. So now I'm going to do a little bit more of a slightly deeper dive on some of these domain-specific languages that I just mentioned here, to kind of give you more of a flavor of what we're looking at. So first, I want to talk to you a bit about Peak, which is our PE specification language. So a Peak specification is a Python program which uses the specific types highlighted in red and a well-defined set of operations on those types. So we will use these types in a special way. For example, the PE shown here is a very simple processing element with just two instructions, add and. The opcode is specified as an enum type. This is if you're looking on the left here where it says class opcode. And the instruction, which will include the opcode, is specified using an arbitrary algebraic data type, namely essentially like product types or sum types, also known as like structs and unions. And we have a way to specify that in a kind of arbitrary manner that can be able to be assembled into real hardware bits. And so this is essentially like kind of writing your ISA specification. And there are other fields in this instruction for this particular PE that control, for example, whether to invert the operand A, or to scale the other operand B, or to register the output.
Yeah, it's curious because it looks very similar to PyRTL or PyMetal in some way.
Yeah.
So how do you distinguish with those ones? Or what's the difference? What's similar?
That's a good question. So I think the differences will be immediately apparent on the next slide. But this is those are mostly just. So I might be unknowledgeable about the real extent of what they can do. But one of the important things that we're going to get out of this is that not only can this be interpreted as RTL, it can also be interpreted as a functional model, and it can also be interpreted symbolically, so that we can get a pure symbolic expression for kind of formal work for this specification. But I do agree that it might look similar to some of these other RTL design tools. And in fact, this looks very similar to our Magma tool, which has the ability to specify things like this.
Okay.
The other things I'd be interested to see if it has this kind of arbitrary algebraic data type specification for some of these other tools. That's actually one of the most useful features from this, is to be able to kind of really arbitrarily specify these ISA descriptions, especially sum types. So note that the operands. Note that the operands that the PE is computing on also have a specific type, in this case 16-bit unsigned bit vectors. And then the PE itself is a very simple class with two methods. The init basically just defines all your subcomponents, including state, such as registers, memories, or other hierarchical peak components. So very similar to kind of like a hierarchical RTL module design. And then the call method takes as input the instruction and the operands, this case A, B, C, and Cin, and updates the state and produces outputs. In this case, the result of an add or an and a flag in case if the add resulted in overflow. So how does this peak compiler automatically generate these different components from the specification? So the answer lies basically in the type system that I just mentioned. So peak program uses abstract types provided by the peak DSL, such as bit and bit vector, et cetera. And each component of the peak compiler, like the RTL generator or the SMT context, provide a separate concrete implementation of these abstract types. So one can view this as multiple interpretations of peak specification in different contexts. So in a Python context, one would use the Python bit vector implementation and generate a functional model. So A plus B literally returns the sum of A plus B, like if you evaluate that in Python. In Magma context, one would implement abstract bit vector using Magma's notion of bits, and it would generate RTL. So A plus B in that code would literally stamp out an RTL instance of an adder with the inputs tied to the inputs A and B. And then in an SMT context, one would use a quantifier-free SMT bit vector implementation and generate a symbolic representation. So A plus B would return the symbolic expression A plus B represented and using SMT. And that last one, as I'll show in the next slide, is used to automatically generate rewrite rules. So I won't go too in depth into this as we're trying to publish on this. So we were using a synthesis-like technique in order to generate the appropriate rewrite rules automatically for Core IR. As Core IR has formal semantics in terms of SMT. And so essentially you can think of it as you were able to construct an SMT query that when solved will produce the appropriate rewrite rule for a particular primitive to whatever our specification of your PE, if that makes sense. So that's Peak. Now I want to mention a few of the other languages within our ecosystem. So first, Magma is our hardware construction language. So essentially, it's a Python embedded DSL, which you can use Python to meta program and to construct these Magma circuits. So in essence, this is exactly analogous to Chisel and Scala. So Chisel is a embedded language in Scala that allows you to use the full power of Scala to generate Chisel circuits. And it has a similar class-based descriptions of modules and allows you to use the full power Python metaprogram it. Here's the example of side-by-side comparison of writing a full adder in both Magma and Chisel. And as you can see, they're pretty similar. And this is basically a structural representation of hardware with obviously the additional beneficial syntax of being able to use inherent operators like and XOR, et cetera. We can also specify sequential circuits using some convenient syntax. And this actually looks very similar to the peak representation, where you essentially define all your subcomponents and your state within this init block. And then you can use call to essentially describe the FSM style update and a next state computation for your circuit. And then some other Magma features. We have interesting higher order operators like fork, join, fold, scan. Pat has been particularly interested in like generating systolic arrays using these higher order operators, which is pretty cool. We have kind of methods to do Verilog templating. So if you ever use like a tool like Genesis, which kind of has a Perl wrapper on top of Verilog, we have the equivalent of you can kind of template metaprogram Verilog using Python and embed in Magma. And we also have a nice way to kind of do source code integration of Verilog into Magma. And then also have a kind of standard, we call it our standard lib of circuit components, which includes a whole bunch of generators and circuits to do basic things like comparison, multiplexers, decoders, sequential logic, memories, etc. And I suspect that this is probably similar to, I think that you guys have a Python-based HDL that might be similar to Magma.
Yeah, but the name is like a little confusing. We shouldn't have called that. Pyrope is a stone similar to a Ruby. That's no connection with Python.
Oh, okay, sorry. I definitely misunderstood that.
Yeah, we should maybe change the name, but we use it for historical reason. It's not connected to.
Gotcha.
The Pi is not Python based.
I see. Out of curiosity, what is the Pi then?
When we started in our group, we used to do Ruby, not Python. And there is a stone that is very similar to a Ruby that is a Pyrope. It looks like a Ruby.
I see.
And we started to work on that. The language have evolved, no longer looks like Ruby.
Gotcha.
But that's the origin, and we kept the name.
That's funny. I learned something new. Yeah, so that's kind of Magma. Magma is Lenny Trong. He's a student in Pat's lab as well. And any deep questions about Magma should probably go to him, and happy to put anyone in contact if you want to try out Magma.
Just curious, because it's on the Magma, the PyRTL team, which has some similarity, they generate an intermediate representation. So here from Magma, what do? Do you target directly IR?
So we
core
target
IR, or what do you do?
So Magma has some basic Python structural IR that it kind of keeps in its representation, and then it will compile to core IR.
So, but core IR is a C++. So how does it do? You have a
we have
Python embedding, or
so core IR has a Python API associated with it. But again, so you're correct in the fact that Magma itself has a Python-based representation that is staged there before it will compile into core IR.
Okay.
It's not just using the core IR constructor on top of Magma. So Magma has its own kind of some higher level features, because there's a lot. I didn't go into depth on this, but there's a lot more interesting kind of type level stuff that Magma can do. That is higher level than what core IR would be representing.
So in the core IR, it's more when the interface is more like a control flow or AST, or it's more like a flow graph.
Yeah, so Magma does have a representation of a control flow AST, and actually they basically use this, what kind of looks like this call function here. And so they have ability to kind of maintain that through the compilation flow if we really want to target always blocks. We also have a mechanism to generate always blocks from kind of more of a structural representation that will happen at the core IR level. But yeah, there's a whole bunch of different kind of options there to go through. But fundamentally, it does look structural, the Magma representation.
Okay.
So the other tool I want to mention, because I love this tool, and this has kind of saved us a lot for the verification effort, is this tool called Fault, also made by Lenny, which is a Python embedded hardware verification language. So towards the goal of improving validation productivity, Fault was developed, and it is integrated with Magma, which allows verification to be done at the same level of abstraction as the design code in Magma. And Fault importantly supports metaprogramming so that the verification components are as flexible as their design counterparts. And finally, Fault is designed for portability, which increases verification productivity by allowing users to easily migrate between verification tools. So we could target either Verilator or NCSIM or something like that to find one for the appropriate use case with the same exact tests. So because Magma allows metaprogramming circuits, test benches themselves need to be similarly metaprogrammed to cover the space of the generated circuits. So for example, on the top, you write a parameterized function in Python to generate a circuit. So this is a very just simple example of a possible circuit that basically takes in two inputs, and then you parameterize it by some sort of op, so you can pass in an add or multiply or something like that, and then it will return the result of that. So the classic generator, essentially, a binary function generator. And then in fault, we write essentially an analogous function. So basically the parameters to the circuit generator are the same parameters that go into the fault test bench generator. And then you can basically build up a sequence of verification commands like peek and poke and eval and expect and all these things in order to test the particular instance of the circuit. So note, this is not testing the actual generation code. It's testing, it's a general way to test a instance of the generation code. So if you pass in a particular op, you can test that op. But this makes yep.
So to understand, so in this example, it looks like you leverage that type inference from Python so that you can change the sizes, and then you allow, for example, you could change the bits instead of 16 to 8.
Yeah, you can.
And they will instantiate in a different way the object. Is that correct?
Yeah, exactly. I mean, you can. I mean, we didn't do this here, but you could imagine that 16 in there is also a generator parameter. So that could have been parameterized out as well, and then the test bench is there. So, but the high level concept is that the same parameters that you would pass into the generator, you would also pass into the test bench in order to test a particular version of the generated module. And the way this works is we essentially fault uses an architecture where execution is performed in stages. So in the first stage, the Python program is executed to construct essentially this fault program. And in the second stage, so fault has its own kind of intermediate representation for all these verification primitives like peek, poke, and expect, and all these things. And then that representation is compiled and run in a target environment. And as you can see, we support a good chunk of environments, which has been super useful.
So one question I have, because one of the focus that we have in our group is trying to be incremental.
Yep.
But in this flow, you sort of create an executable, and when you execute this Python, you generate all the source code. So it kind of makes it kind of tough from an incremental point of view.
Yeah. There's definitely trade-offs.
How do you deal with those things? And yes, there are always trade-offs. But what is for example, for the large designs that you have, how much time does it take until you get an answer that you can start to iterate? Obviously, you do a GCT, it's going to be seconds or nothing. But I'm talking, if you do a big ML array of inference with a big design, how long does it take, or how do you handle this issue with the time that will take you to generate the circuit?
So I mean, we have an ability to basically, if you're not changing the circuit itself, like the appropriate, like for example, in the Verilator or the Verilator test bench, which that's kind of our main developing tools to try to use Verilator as much as possible until we really need to use an actual commercial tool. So we can leverage the Verilator generated circuit while still changing the test bench, for example. So a change in the test bench does not necessarily require a full recompilation of the entire circuit. If that makes sense.
So you leverage that it's a CGRA and that you don't have to change so much the CGRA structure. But
well,
you
it just depends on
Pike,
the so
you play with a Pike, for example, that it will change everything.
So just to be clear, fault is a generic tool. Like it's not necessarily just targeted for the test or for CGRA, and we happen to use it extensively to unit test a whole bunch of portions of the CGRA. So like, for example, when we're testing each individual PE, we have a whole giant set of unit tests written in fault in order to target just the PE, and so on. So yeah, I just want to note that this is kind of a general hardware design tool that's not necessarily just for the CGRA. But in terms of the software infrastructure, yeah, I mean, there's definitely some interesting questions in terms of like, what is the most efficient way to do incremental recompilation? If you change one portion of your circuit, you obviously don't want it. You don't want it to take too long in order to recompile that entire thing. Okay. And that's actually something that I've been looking a little bit at CoreIR, but there's definitely a lot more work to be done there. And I would be actually very interested to know if your group has come up with some very good solutions to the whole incremental compilation problem.
Yeah, so we are working on incremental, and we have some DAC papers on that. And then the other thing is now we are trying to focus on more multi-threaded. Core IR is multi-threaded during the compilation or not?
No, unfortunately. I would love it to be multi-threaded. I haven't had a chance to update that though.
I think Jose also left out one of the bigger things we kind of come across is, there's kind of this fundamental challenge of when you have a embedded DSL that, for that thing to do its generation, it has to basically run the program. And once you basically create that full-size program, you've basically lost any chance of incremental. And so embedded DSLs, the perk, of course, are easy to get going, but the cost of things like incremental, it's perhaps harder to be incremental than it would be if it was just native source. We could like dip the files and quickly act on it, right?
Absolutely.
So, yeah, this is a challenge we've been talking about for a while. And so we have some current brainstorming ideas on this issue.
Yeah, I mean, this is also, this is kind of inherent to the just structure of a generator, I would claim, where you have to run that generator in order to produce the source code. There's also other major issues that we've been running into in terms of like symbol tracking and for debugging purposes. So if you have one line in your original generator code that is executed multiple times to produce different portions of the circuit, which happens often. If you have a for loop, for example, stamping out a whole bunch of instances, then all those instances are going to be mapped to the same line number essentially for debugging purposes, if that makes sense. So there's a whole host of kind of interesting generator-based kind of research problems, I would say, in this space.
Definitely sounds good.
Yeah, and the last one I want to go through is Core IR, which I'm not a language. It's more of it's a hardware IR and compiler framework. Probably similar to, I know you guys have LGraph. Is that the right?
Yeah, so we have two representations, like higher level, which is LNAST, and the lower level is LGraph. The whole project, we call it live, actually.
I see, yeah.
Live hardware development, but yeah.
Yeah, and there are a few other IRs floating out there, like Fertile. There's LLHD, and there's a whole bunch of kind of these IRs that are floating out there. So just in terms of Core IR, basically I started in 2016 with the goals of being explicitly interoperable with Python. Magma was actually the first tool to come out of us, literally code by Pat because of his frustration with the design. So he started Magma. So I developed Core IR to first class be compatible with Python. So made all the C APIs and all that. I was very, very interested in linking IP, specifically parameterized modules and generators. So there's a couple design decisions in Core IR that I made that kind of facilitates that. And then the thing that became abundantly clear as time went on for anyone to use our tools was to generate high quality Verilog. And so probably one of the, I would say the biggest benefits for Core IR is we spent a lot of time and effort creating good quality Verilog generation from Magma and from high level source code, from high level source code, and like kind of yeah, there's a lot of fun tricks that we've played in order to get high quality Verilog generation, because that's the biggest complaint of anyone trying to look at the Verilog code at the end. That was one of the things that kind of I know was an issue when Google tried to use Chisel, was that the quality of the Verilog was not very good. So we put a lot of effort into that. And then also a first class was integration with formal tools. So I basically designing Core IR for it so that its primitives were kind of one-to-one. Actually, yeah. So just quick thing here. So like Core IR kind of have a different, in some sense, I really like the RISC-V kind of design of having essentially a kind of a base primitives or a base thing, and then you have kind of extensions on top of it. So the Core IR's base primitives are one-to-one with the Core IR, or with SMT quantifier-free bit vector semantics. And then we also have a floating point representation, which we've been using in the CGRA. So we have some floating point stuff in there. And then we've been working a bit more on getting SMT arrays to map nicely to the semantics of memories. There's still a bit more work to be done there. And then kind of a common set of other random library components here. And then last, I just want to mention one things I've been working on. I'm not sure if you you probably are familiar with the MLIR circuit endeavor that's been recently out of Sci-Fi and with Chris Latner and all of them. So I've been, I suspect that will be an important open source hardware tool in the future. So I'm trying to be compatible with that. So essentially creating a MLIR core IR dialect in order to essentially round trip all our code to that ecosystem and back. I think it would also be interesting to see if there would be a way to interact with your code base at some level. I suspect that probably would be a couple days worth of hacking to get something working there. And and then a lot of focus recently on basically maintaining symbols for debugging and physical design purposes, especially through transformations, which is all kind of an inherently difficult problem. And then improving linking flows with generated components, and then just kind of more general optimizations. So I'm actually, looks like I'm out of time. So let me quickly go through my last couple slides. Do you have a couple times, or actually I could stop right now and we can take questions.
No, you can continue. It's okay. You go a little bit over time. That's
Sorry,
okay.
yeah.
No problem.
So final notes for at least the meta-compilation stuff. So this approach is complicated, but I think worth it. And we fundamentally need a quick iteration in hardware design in order to move forward here. And incrementally abstracting portions of a manual design and compiler is still useful, because at the end of the day, it will still decrease iteration time. Because the less you have to manually encode some of this stuff, the better it is, even if you haven't gotten all of the way there to a pure generation. So we've made a lot of progress, but there's still lots to do. So for example, this is our real version of our compiler flow. I showed you kind of like the hand wave version of this, and there's still some hard-coded stuff. And even worse, there's actually one portion of the flow where we have a grad student who is actually manually doing translation of a portion of the flow. So we're almost at a pretty good point here, but not quite there. And there's still a good amount of work on our end in order to get this kind of meta-compilation flow really working well. But we still have been able to use this flow in order to do, in particular, PE design space exploration, targeting particular applications. So a cool thing that we've done is we basically analyze benchmarks for frequent compute patterns, and then construct viable PEs in an interesting way to optimize for those frequent patterns, and then evaluate area energy performance for each PE design on our benchmark suite. And so just a couple of results slides here just to show that this kind of works. So for example, here you see PE1 through PE5. These are examples of the PE structures given particular frequent subgraphs of all the applications that we want to do. So the PE1 has basically just like the very basic stuff, but this PE5, that kind of structure there is a combination of a bunch of different frequent subgraphs that we see in it. And we expect the area, the total area, or essentially the total number of PEs to go down, and the energy usage to go down, because we don't have to use the routing fabric between each PE in order to do that. And it's all internal. And so as you can see, the number of PEs used goes down, and then similarly, the energy per operation goes down. So some interesting preliminary results there. But we really want to integrate this with generalized memory and routing in order to really get a good result. So that's all I have. Thank you, and I'm happy to answer any other questions.
Thank you very much for the talk. Something that I'm curious to see, what is your opinion? You were mentioning like the clapping. Something that you were mentioning, and so there's Fertile, there's Circuit. Mm-hmm. Those are the main ones. LHD.
LLHD, yeah.
That's a different one. But
also Circuit. Yeah, sorry, go ahead.
How do you compare with Circuit and Fertile?
Yeah, so Circuit.
Because those are the ones I know more.
Yeah, so well, just to be clear, Circuit is a set of kind of representations, and there's not a particular representation. I mean, and also that is still absolutely in flux. That was started 6-ish months ago, and there's a lot of work that they still need to do on that. And I'm not sure if they even have a full compilation flow working there yet, but it's clearly there's a lot of people interested in working on that. So it's kind of a bit hard to compare to that. They have the interesting thing in my mind about MLIR and Circuit is just the ability to describe different levels of kind of IRs very easily within the same exact framework. So they have this kind of like handshake level IR, which has an elastic timing model. They have like a particular system Verilog, essentially AST-like representation embedded in there. So there's kind of like, it's very cool that there's that meta framework that allows you to easily integrate all these kind of different dialects. I think they call them dialects there. And then in terms of like their actual structure of what they're using for their like kind of core structural level IR there, I think right now they're basically using either Fertile or LLHD for that purpose. And it's probably about 1-to-1 with one of those. In terms of comparison between Fertile and Core IR, I mean, functionally they do similar things. To put it bluntly, like anything that you can represent in Fertile, you can represent in Core IR. I would claim that you might be able to represent a little bit more in Core IR than Fertile, because I can represent basically black box generated modules, and I don't think that Fertile can do that. But yeah, I mean, there's at the end of the day, it's just kind of like a different representation of the same thing. The other thing is,
do you, for example, do you have attributes? Is one of the things that there was
yeah,
for with the attribute thing.
Sorry, I didn't mention that, but the ability to add metadata and attributes. I know Fertile has done a lot of that, and I mean, Core IR you can add arbitrary metadata as long as it's serializable, but there could probably be a little bit more work done on just a better structure of that for kind of the things that you want to represent. But you can kind of add arbitrary data there.
I really appreciated your figures. Help me try to put together all these projects we're on at Stanford, because I've heard these talks mentioned and trying to see how they all fit together. The one I didn't see there, which I understand maybe is related but not the same people, is spatial. How does that fit in?
Yeah, spatial. So that's Kunle's group.
Yeah, exactly.
Which is a bit orthogonal to our group, but that's a good question. We get this asked.
The reason I'm asking that is not so much the hardware design, but more the CGRA aspects, right? That's also, I think,
so they have an interesting CGRA. It's a very similar CGRA design. They have an extra level of hierarchy essentially in their core design where you kind of have these kind of bigger style. I forget what terminology they use there, where you have these. Imagine like our island style CGRA stamped out a couple different times, and there's some second level memory in between each of those. They also have embedded like address calculators in there as first class, whereas we kind of are a little bit more flexible on whether or not we have that. So in terms of like I suspect that our framework could probably represent the plasticine is the name of the architecture that they're using there. And I know less about their kind of total parameterization space on their architecture. But in terms of spatial is kind of like it's like halfway between an IR and a language for representing their programs. And it seems like a useful thing. And there's actually an endeavor to be a little bit more interoperable between our group and their group. So potentially be able to compile spatial to our CGRAs and then be able to compile our halide to their CGRAs. So yeah, unfortunately, it seems very much overlapping, especially because we're both at Stanford and within the same CS department. And honestly, there probably could have been a bit better conversations happening about 4 years ago in order to kind of more facilitate collaboration between these two groups. But they're just fundamentally different projects.
Yeah, I appreciate the answer. Exactly. I've seen both from the outside. I was curious if there's any. It's exactly right. Some sort of IP transfer for the.
Oh, sorry, I think I can't hear you.
Oh, I was just saying. Thank you for clarifying. Because yeah, I've heard about both things in conferences and such.
Maybe I lost it, but I still can't.
I can hear you. So I can hear you well. So I don't think you should be cross side.
Is this on my end? This could be on my end.
Yeah, I think so.
Is this better? We try again.
Oh, sorry, I can hear you now.
Okay, great. Okay, so
sorry about that.
Oh yeah, thanks for explaining that. That was really helpful. Because yeah, I've heard about all these things at conferences, and I was just curious if, because I was aware from prior publications that the plasticine lineage had implementations, and I was curious how the implementations, if they were converted, or it sounds like they're completely independent of the ones you guys are doing in AHA. It seems like so. Yep. Cool. Wow. Yeah. Embarrassing riches.
Yeah, I mean, one of the things between that group and our group is that they're very Scala based and we are very Python based, which creates a rift initially.
Yeah, that's something I'm sure maybe you talked to Lenny about. So Lenny, of course, for those who don't know, is an undergrad at Berkeley working with us on the CGITS team.
Oh,
so
cool. I didn't realize you knew Lenny. Yeah.
Yeah, no, so I was formerly in Berkeley on the CGITS team in Python. And
Cool.
so that's kind of thing. So there was Berkeley doing Python CGITS, Stanford was doing Delight and Scala. These are competing projects. And then years later, we switched languages. We go to Scala and they go to Python. We're like, the grass always seemed greener, I guess.
Yeah, exactly.
Scala's had its share of headaches. Yeah. I'm curious, so have you had any headaches using Python, dynamic typing for your guys' DSL works? I don't know if maybe it's error checking or things like that, or
I would say it's a little bit more fragile. Like it's like if you get a Python bug, especially because a lot of the stuff that we're doing, we're kind of doing some very hacky stuff like execing generated code within Python in order to get some of these abstractions to work just very nicely out of the box. And oftentimes that inherent structure there is hard to debug if there's a bug that shows up later on in the flow, and then you have to try to go back to that source view of that. Python is a little bit awkward, especially for some of the really weird stuff that we're doing. So that's one aspect of it. But I mean, one thing that we've been pretty good at is doing like, I mean, you could kind of put this in the agile mindset of doing a whole bunch of like code reviews and like kind of treating this in some way like a real almost startup-y like project where we try to like I don't know, we have type annotations on everything in our code base and just try to make it high quality so that those problems don't show up as much. But in general, I would say that's kind of the only major issue is just the fact that it's so flexible to do almost anything in that language. Then there could be some hard to debug parts of our infrastructure.
But there seems to be a fundamental problem with these transpilers, right, from source to source, right? We had these problems with CGITS, we had these problems making chisel. It's not just for debugging, even just giving people sensible error messages, right?
Where absolutely, that's absolutely true too.
It's not just identifying the source line, it's also catching the error at a point in your flow where you haven't lost so much information and can tell them intelligently what the cause was. And so actually, I would argue a decent amount of complexity in a chisel code base isn't really about writing chisel or generating fertile. It's just getting early enough in the Scala machinations to catch these kinds of things. Use Scala macros in order to catch these things early on. Otherwise, we would never have a need for macros in the project. I don't know if there's a similar headache in Python where you're trying to catch a user error early on and give an appropriate warning or error message. I don't know if that's tricky or harder.
Yeah, so I mean, in general, my mindset has always been like, just put as much assertions and code in, or that kind of checking code eagerly into the code base to error out as soon as possible, just to make it much easier to debug. Although some of those things end up not being as Pythonic as we want in kind of an arbitrary thing there. But yeah, I mean, I would say just like the debugging of the infrastructure itself and the error message and that kind of stuff has been kind of the main headaches. But it's super. I think there's a lot of stuff that we're doing in Python that would be very difficult, if not impossible, to do in Scala.
Probably true. Cool. I think it's like Jose had a question. I didn't mean to cut him off.
Yeah, so I was curious. So now we are fighting a little bit, like interfacing Fertile and things like that with our flow. And one of the questions is there that is I was checking with LHC and the other ones, is when you translate to core IR, you already have to have the bit size set. Is that correct?
Yes. So core IR. So the semantics of core IR is essentially the same as these like SMT bit vector primitives. So that's actually a major difference between Fertile and core IR. For example, is like I know in Fertile you can have an add on 2 arbitrary bit widths. And that will be represented in that code, whereas in core IR that's not the case. That translation has to be done up front in order to concretely determine the bit widths of everything.
Okay, so it's similar to LHD that you also have to do that ahead of time.
Yeah, exactly. That was actually one of the major things that we decided up front, because also that just is like really nice, better integrates with formal tools than having these more flexible kind of decisions. And in fact, we do have the ability to do that, but that's at the level of Magma. And this is kind of the typing I was talking about in Magma, where you can actually do those kind of things where like RTL designers really want that. Like that was actually a major pushback in terms of these representations when we were getting actual designers to use this code. Also, just to mention this, we've used Magma and Crier to tape out a chip at Facebook. Lenny's working at Lenny and another student, Raj, is working. Been working kind of part-time at Facebook, and they've been using some of our tools in order to tape out a real chip. So we actually do have a real chip under our belt, which is kind of cool. And and it's been great because we get feedback and pushback on our tools from like actual industry RTL designers. And that was actually, yeah, just to bring it back, that was one of the major complaints was that precision in that required precision for specifying all the bits or all the sizes of every single signal in the design. And so one of the features of Magma that has been recently introduced is the ability to kind of be a little bit more flexible in that and then do a bit better type inference.
So, but on Magma, because it's Python, I guess that you do the DAG type inference, and it will propagate the object in Python, and then you will have some way to decide when the program executes what's the bit size. Yeah.
So there's multiple different ways to do this. Like a lot of it is just like fancy operator overloading in Python in order to do the appropriate thing. There's one case I think where you can't just do operator overloading, and you really need the semantics of more than like I forget exactly what it is, but there's some fancy tricks that need to happen in order to get a lot of that working. But for the most part, it's kind of pretty easy native Python code.
Okay. Yeah. Cool. Now I didn't mention, but on the SMT, I'm pretty sure you use CBC4.
So I mean, one of the things that we have. So first of all, we have Clark in our group who basically wrote CBC4, and so we have a couple tools that really try to be independent of whatever the solver backend is, and just take in kind of abstract SMT representation. Then you can choose what solver that you're using there. So we absolutely have the ability to use CBC4 or Z3 or Boolector or whatever other thing. Formal tools that we have available in whatever system that we're running it.
And the main use that you are doing is the thing that you were mentioning looked like a little bit like the Raspberry work that it does with a skeleton for program generation. But for what else do you use the formal checking tools? Yeah. So I mean, we will do model checking directly on our designs and proper checking and all that. And then this rewrite rule generation was just a way for a cool way for us to use these formal tools in order to kind of automatically do this synthesis. So that was one example. We also have a couple of things coming up where we're using some SMT-based analysis to do interesting optimizations, but that work's not out yet. Okay. Let me see if there is any question from the audience. No, I guess I like to make a lot of questions. So there is anything else from anyone else? No. So thank you very much for doing the talk. Thank you for having me present here. I noticed and I have the video off all the time. And I'll have to schedule something where one of you can talk about your work at our AHA meeting. Okay. Yeah, after micro deadline, that should be fine. Yep. Okay. See you. Good. All right. Thank you.
Thanks again. That was a great talk.
Thanks. All right. Have a good one.
You too. Bye.